Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand intellectual edifice of modern biology, D'Arcy Wentworth Thompson's 1917 magnum opus on growth and form stands as a magnificent, solitary, and somewhat eccentric tower. It is a work of profound erudition and breathtaking scope, fashioned from the unlikely materials of classical scholarship, pure mathematics, and physical science, published in an era when biology was becoming ever more fixated on the mechanism of natural selection and the tracing of phylogenetic lineages. Thompson's book offered a powerful and elegant counter-narrative. He proposed that the forms of living things are owed as much to the universal laws of physics and the constraints of geometry as they are to heredity and adaptation. For Thompson, the organism was a physical object before it was a historical one, its shape governed by the equilibrium of forces, the minimization of surface tension, and the mathematical logic of its own growth. It was a perspective so grand, so classical in its search for unified principles, that it appeared almost alien to the prevailing biological thought of its time, a message from a parallel scientific universe where Plato and Archimedes held as much sway as the intellectual soil from which on growth and form grew was a landscape of competing biological philosophies. The dominant paradigm was, of course, evolutionary. The work of Darwin had provided the great organizing principle of descent with modification, and biologists like Ernst Haeckel were meticulously charting the family trees of life, seeing in every anatomical feature a clue to ancestral history. This approach, while immensely powerful, tended to view biological form as a purely contingent outcome of selective pressures acting upon random variation. Thompson found this explanation incomplete. His classical education had instilled in him a deep appreciation for universal forms and ideal types, while his mathematical training gave him the tools to describe them. He saw in the work of predecessors like the Belgian physicist Joseph Plato, whose experiments with soap films revealed the principles of minimal surfaces, a key to understanding cellular aggregates and the shapes of simple organisms. He drew inspiration from Galileo Galilei's discourse on the scaling laws, which explained why the bones of a giant must be proportioned differently from those of a smaller animal, a foundational insight into the relationship between size and shape governed by the immutable logic of the square-cube law. This law stipulates that as an object grows, its volume, which can be thought of as proportional to the cube of its length, increases faster than its surface area, which is proportional to the square of its length. Thompson saw this simple ratio as a powerful constraint shaping the entire tree of life, dictating the maximum size of an insect, the necessity of convoluted surfaces in lungs and intestines, and the very architecture of existence. Thompson's method was to treat the living organism as a problem in physics and engineering. He examined the hexagonal structure of the bee's honeycomb, demonstrating with mathematical rigor that this geometry provides the maximum storage volume for a minimum of wax, a solution to a problem of optimization that would delight any engineer. His analysis of the microscopic skeletons of radiolarians revealed forms of stunning geometric complexity and regularity, shapes that echoed the symmetries of crystals and the surfaces of liquid equilibrium. Perhaps the most celebrated example of this approach is his analysis of the human femur. He observed that the intricate internal latticework of bone, known as trapeculae, aligned precisely with the lines of stress and tension the bone experiences under load. He then juxtaposed an image of a femur's cross-section with a diagram of the stresses in a Fairbairn crane, a common industrial derrick of his day. The correspondence was astonishing. The trapeculae formed a pattern nearly identical to the girders and supports of the crane, revealing that evolution, through its process of incremental development, had arrived at a solution of optimal mechanical efficiency, a solution dictated entirely by the laws of mechanics. The bone, in this theoretical diagram of the forces acting upon the intellectual centerpiece of On Growth and Form, and its most enduringly famous contribution, is the final chapter on the theory of transformations, or the comparison of relative forms. Here, Thompson introduced a revolutionary technique for the study of comparative anatomy. He proposed that the differences in form between related species could be understood as a systematic, mathematical deformation of a Cartesian coordinate system. He would draw an organism, for instance, a common porcupine fish, within a simple rectangular grid. Then, by applying a consistent mathematical transformation to the grid itself, for example, by shearing it or by logarithmically expanding one axis, the image of the organism contained within would warp into the precise form of a related species, such as the ocean sunfish. This was more than a clever visual trick. It was a profound conceptual leap. It suggested that the vast diversity of life was an expression of variations on a mathematical theme. The transformation from one species to another could be described by a concise mathematical function, where a new coordinate x prime is a specific function of the original coordinates x and y, and a new coordinate y prime is another function of x and y. This method reframed evolution, the difference between a baboon skull and a human skull, or between a fossil ungulate and its modern descendant, could be represented as a consistent change in the underlying field of growth. This geometric perspective implied that evolutionary change proceeds along mathematically defined pathways, with development being guided by a global system of differential growth rates. It transformed morphology from a catalogue of static shapes into the study of the dynamic processes that generate them. The immediate reception of Thompson's sprawling masterpiece was one of immense respect mingled with profound bewilderment. It was universally praised as a work of literary genius, a monument of scholarship that roamed effortlessly from the dialogues of Plato to the physics of droplets. Peter Medawar, a future Nobel laureate, would later describe it as beyond comparison the finest work of literature in all the annals of science that have been recorded in the English tongue. Yet, for the practicing biologists of the early and mid-20th century, who were busy forging the modern synthesis by uniting Darwinian theory with Mendelian genetics, Thompson's vision felt peripheral. His work seemed to lack a tangible mechanism. He described the mathematical patterns of growth with unparalleled elegance, but the genetic and molecular machinery driving these patterns remained a black box. His emphasis on physical forces and mathematical constraints was perceived as a challenge to the primacy of natural selection, placing him outside the mainstream of evolutionary thought. His ideas were embraced more warmly by architects, designers, and crystallographers, who saw in his principles a universal grammar of form that transcended the biological realm. His influence can be discerned in the structural logic of modern architecture and the pursuit of organic forms. In industrial design, the full vindication of Thompson's vision would await the dawn of new biological disciplines decades after his death. The rise of developmental biology, and especially the field of evolutionary developmental biology, or evo-devo, has revealed the very mechanisms he could only infer. We now understand that genes, such as the famous Hox gene family, act as high-level switches that control the rates and directions of growth in different parts of a developing embryo. A small change in the timing or location of a gene's expression can produce precisely the kind of coordinated, global transformation that Thompson depicted with his deformed grids. His mathematical transformations are now understood as macroscopic readouts of underlying genetic and developmental programs. Furthermore, his physicalist perspective found an extraordinary, if unwitting, successor in the work of Alan Turing. In his 1952 paper, The Chemical Basis of Morphogenesis, Turing proposed a mathematical model, based on reaction diffusion equations, to explain how patterns like spots and stripes could emerge spontaneously from the interaction of chemical morphogens. Turing provided a plausible chemical engine for generating the biological forms that Thompson had described with the language of geometry. The two great British thinkers, approaching the problem from different ends, had converged on a shared vision of life as a pattern-forming system governed by mathematical law. Even the digital age owes him a debt. The morphing effects seen in films and computer graphics, where one image seamlessly transforms into a direct technological implementation of the principles laid out in his theory of transformations. In conclusion, On Growth and Form remains a work of singular importance, a timeless meditation on the interplay of physical necessity, mathematical order, and evolutionary contingency. D'Arcy Wentworth Thompson did for biology what Isaac Newton did for the heavens. He demonstrated that the same physical laws that govern the shape of a soap bubble, the splash of a liquid, and the structure of a crystal also sculpt the living forms of a radiolarian, a femur, and a fish. He revealed that evolution operates within a universe of profound mathematical structure, its creative power channeled and constrained by the elegant and inescapable logic of physics. The book is an intellectual monument that challenged a generation of biologists to look beyond the particulars of adaptation and to see the universal principles at play. Its legacy is a testament to the idea that a complete understanding of life requires a synthesis of disparate ways of knowing, a union of the historical and the physical, the contingent and the necessary. It is a powerful reminder that the story of life is written in a language of both genes and geometry, a cosmic dialogue between growth and form.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.